did already see the Fourier transform.
The quantum Fourier transform.
Okay. Just to know if it is going to be boring for the 100% of you or for only part of you. So there is still somebody who didn't study the quantum Fourier transform. Okay. Then, yeah, good afternoon, everybody. So then today we have, in these 2 hours together, we are going to study 2 things. The first hour is all about the quantum Fourier transform, and the second hour is all about the phase estimation, which uses the quantum Fourier transform as a primitive. And both these 2 are used as primitives in Shor algorithm that tomorrow Martin Ecker will explain. So we are going to have a direct use of what we are going to do today in tomorrow's class. So we can start. Okay, so you all know about the standard Fourier transform that is defined as follows when it's with the discrete variables classically. So this is a classical, purely classical mathematical expression. And you know that it finds application in several contexts, in particular in analysis of signals, when you want to find the periods of a certain signal, and then it's useful to do the Fourier transform to discover what is the frequency content of your signal. And by the way, this is also how it is used in Shor algorithm, as you are going to see. But then, and also like typically in physics, you study, it's useful to study what happens in the momentum space when you start from a certain spatial distribution, for instance, in a lattice. Say, for some of you is taking classes of condensed matter, so it's also something that it's used in there. It has many applications. So then the quantum version of this formally is written very similarly. I'm going to write it. So you can start from state J and consider the quantum superposition of all the worlds and I think that by now you might be familiar with the notation that we are going to rewrite anyway. I don't remember if I didn't introduce it myself, maybe Anton did, where this J is a collective qubit register. And it corresponds to the binary representation of the number. So what you say is that J is equal to the 2 to the, so let's say, J1, 2 to the n minus 1, plus J2, 2 to the n minus 2, plus Jn, 2 to the 0. So for instance, if you want to make an example, the number 5 is represented as 1, 0, 1 on 3 bits. Then you can then write this in a quantum register associating qubits in state 1, 0, 1. This would be because this is 2 to the power 2, which is 4, plus 0 times 2 to the power 1, plus 2 to the power 0, 1. So it's 4 plus 1, which is 5. So then what we are going to do during this lecture is that we are going to construct explicitly a quantum circuit that does this. And then in the second hour, we are going to use this state preparation to do phase estimation. What I wanted to make you observe is that what this does not do, so this does not compute the Fourier transform, the classical Fourier transform, because it is true that formally, mathematically, the expression looks alike, but you cannot access with measurement these amplitudes. So it's really not helpful to compute the classical equivalent of the Fourier transform, but it's a useful quantum state preparation to then use it in quantum algorithm, as I said, like a SHOR. Okay, so what we're going to do now is how to do this and show that it's quantum so efficient in time. Yes.
It's J dot K. Is that
is the standard what we, I don't know if we had been...
J1, K1 plus...
Yeah, it's a J1, K1 plus J2, K2 plus J3, K3, maybe I can write it here. Okay. So with this we follow completely the Nielsen and Chang today. So everything what I'm going to write is appears on the Nielsen Chang. So before going to how to build this with a quantum circuit and show that is efficient in the sense that you can do this with a polynomial number of gates, we're going to rewrite this expression because then it will make more apparent how to choose a circuit. So then we are going to do a little bit of mathematics and rewrite this expression here. So first we are going to write K. There is another thing that I would like to introduce. Maybe I can do it here. It's a notation. So like in the same way as we have introduced this notation for the binary representation, we are also going to introduce a notation that Nielsen and Chang use that is called the binary fraction. And all what we are going to do today could be done without doing that. But it's a good excuse it allows to rewrite expression in a bit more compact way, and it's a good excuse to introduce it here. Maybe it can be helpful in other occasions. So then the binary fraction is just taking, so let's say first make an example. So this is just J1 over 2 plus J2 over 2 to the 4 plus J3 2 to the power 3 plus Jn 2 to the power n. And then, so in the most general case is the following, where you don't have all from 1 to n, but you have say L plus 1 up to Jm, and then this corresponds to Jl over 2 to the L plus Jl plus 1 to the L plus 1 plus Jm and minus L plus 1. So let's make again an example, like we made the example of the number 5. Let's make an example here to fix the ideas. So if we take, for instance, 0.101, this is a binary fraction representation of a certain number below 1. What is this number? Let's see. So this corresponds to the case where we have, okay, 0 point, a certain J1, J2, J3, which is J to the 2 to the 3 because we have 3 bits, and then this will be J1, 3 minus 1 over 2 to the 3, plus J2, 3 minus 2, 2 to the 3, plus J3, 2 to the 3, and then this is 1 over 2, plus 0 over 4, plus 1 over 6. So then all in all this is 0.5.
You mean 1 over 8?
yes, thanks. Plus 0.125. Then this number is 625. So it's a different way of how to represent a fraction with binary numbers. Okay, so with this we can start rewriting this expression, and we do all the steps. So let me start with this becomes now the left hand side, so I copy it. We have the sum from k equal to 0 to -1 e to the 2 pi k jk over n k. So as a first step, we use that in the same way how we did here, k over 2 to the n. Also, obviously here, capital N, maybe I could write it here somewhere, is the 2 to the n, is the size of a quantum register that can be represented with n bits. So it's how many binary numbers you can represent with n bits. So then first let's observe what is this binary fraction of k. So then this is what we wrote just here. So we have 2 to the n. So this can be rewritten all in all like the sum from L that goes to from 0 to n of kl 2 to the minus L. So the first step is just to replace this here. And then this is going to be replaced with this sum, identifying the capital N with the 2 to the n. So this is an intermediate step. Now we start here again. So this is equal to 1 over square root of n, sum k from 0 to n minus 1, exponential of 2 pi j, and here we have the sum from L equal to 0 to n of kl 2 to the minus L, and then we have our cat k. So this is just rewriting. Then, in the next step, we use that the exponential of a sum is the product of the exponential. So then we replace this sum here with the product of the exponential of this. So let's do that. And the rest I copy. So here we get just the sum. I'm also going to separate explicitly the fact that the k is composed by all of these k1 to kn. So this I can also write as a multiple sum. Kn equal to 0 to 1. And then we have exponential 2 pi j. Okay, so we can do all the steps actually. Yeah. So okay, this intermediate step is just to separate the different k's here. You know, okay. And render explicit that this is a multi-qubit register. And there is still the sum over L. Yeah, there is still the sum. And now we do what I was saying to take the exponential of a sum as the product of the exponential. So I copy all the sums. And then here we product of e to the power j, kl to the minus l, al, where now the product is from 1 to n. Okay, and now we are almost finished. What we are going to do is to separate explicitly the case, what is this index L. Basically, it can be every time 0 or 1. Then we are going to write this explicitly. So then this becomes before. I want to do in the steps. Yes. So we have the product. And from 1 to n. And now we can start by explicitly writing all the terms of this product. So then we have j 2 to the minus n 1. And plus 1, and then we have all the terms up to 2 to the 0, 1. So basically this expression is what we are going to work with, but we can also, so this will be fair enough to be in the quantum circuit explicitly as we are going to do. But then what they do in Nielsen chunk, they take the extra step and write this as involving the binary fractions. So we are also going to do this as defined there. So then this becomes okay, so just one thing, probably I took, so these things, they is not equivalent, sorry. The index goes from 1 to n, so here it should be L first is equal to 1, and then to 2, and then to n. Sorry. Okay, that's better. Mm-hmm.
In that, from the second last step to the last step,
Yeah.
while you remove the summation in the exponential, shouldn't it be JL? Because it's K1 with J1, K2 with J2, and so on.
But, so there is this summation. So then it's like saying that this, no? So then for all the KL, I have to make the product. So that is like saying, say you have K1 plus K2. This becomes K1 K2. And this becomes the product over K of L of KL. If it was only about.
I think, the confusion is that those J, even in just
J
before-
stays there. J, I never.
J is not indexed here, right?
No, it's outside. Yeah, it's outside. It's not an index.
But then when you're doing dot product, it should be J1 with K1, J2 with K2, and so on.
Yeah, that's also correct. But that's also correct. But it's not incorrect what I've been doing here. Like I understand now your question. It's because of this. It's because of this. It is true. But you know, when you have this is also a valid mathematical thing. But it's also your right to keep J here and to
But now K1 is.
and to substitute K with what it is. You can also do that. I just it's an identity. You know, if I tell you, for instance, let's make an example that has nothing to do. But if I tell you, I don't know, 2 times 50, it's my own right to tell you that this is 2 times 10 times 5. And here we are doing the same. So yes, you put so this is your J and this is your K. We have taken K and we have written identities. So if I take K, it is defined as in this way. So if I explicit also that the J is defined in this way, okay, then we have the product and so on. But K is defined like this way, so I can replace it here, and then I can do all the derivation without touching J. It's also valid.
But in this, is there a term called J2K1? Let's say, for example.
Okay, I see what you mean.
I mean, you can go to the first expression and is that now K1, J1 plus K2, J2?
I see what
or
you
it's
mean.
just K keeps changing and the J we
Yeah.
So your question is why the cross terms would be 0? If you would now replace this same expression for, because this is correct. This is correct. Then it's a problem of notation. With because I know that in the Nielsen Chong, usually when they write K, they have in mind the sum of all exactly what I wrote here. So at least there is, what was it, the thing? It was an algorithm, I don't remember if it appears in Deutsche Yoza or somewhere, but you do have this. So here I thought that JK was the same. It would be misleading indeed if here they have in mind the product of the 2 numbers. Maybe here they have in mind the product of the 2 numbers, yeah. Which is different actually. Actually, it is, I understand it, you're right, there is a problem in the notation. It is reflected, I'm really using the notation of the Nielsen-Chong, and it is then, the confusion is really done even in the Nielsen-Chong, because there it's also that they have like this J dot K can be sometimes J1, K1 plus Jn, Kn, and here I understand what you say, that is not equivalent. So here it might be, so this is different than if you take the product of the 2 numbers that are represented.
And here is the numbers.
In here I will use the numbers. So yeah, you're right, good point. So I've been biased because I was teaching, when was it, 1 month ago, to your class, by the way, an algorithm where from the Nielsen-Chong there was this definition. So okay, let's put a big cross, then a red cross even here. And then let's say then that JK is a product of the numbers represented by J and K. Okay. Thank you. Okay, so let's write this as a making explicitly appearing the binary fraction. So then this is going to be 0.j n. And then this is 0.j n minus 1 jn. I will tell you what, we are using an extra step. I will tell you what it is. And here we have J1, Jn. So why are we rewriting this way? This term is easy, you see it immediately, because it's really the definition of the binary fraction that is here. So if you take the binary representation of j and you divide by n, you obtain this directly. From this other, there is a small intermediate step that is saying that, for instance, if you have j divided by 2, like here, for instance, so this, if I write it what it is, the full thing, it will be j1 n minus 2 plus j2 to the 2n minus 3 plus, until the last one, yes, the last one is the binary fraction. So then this one is equal to 0.jn, and then all the others are still having positive powers of 2, and therefore they are integer numbers, and therefore when you multiply them by 2 pi, they do not contribute because they give 1. So then for these all factors, there are parts, so the only part that contribute is the last one, basically, or the last one minus last, and so on and so forth. Because the rest of the number divided by 2 is still not a fraction, is still an integer, and it gives 1 exponentiated with 2 pi. Okay, so then we have these expressions. And now we are in a good position to write down the circuit that allows to obtain this state. Do you have questions? For me, it has taken a while to get, familiar with this binary fraction. It was not at all an intuitive concept, and as I said, you could do everything without. If you do everything without, then you stay here. But it can be good to know that this exists, and that after all is nothing so dramatic. Okay, I will start to draw the circuit for the efficient implementation. That is a very big circuit. So we have here our register with the multiple qubits, J1, J2, Jn minus 1, Jn. And on the first, we operate with a Hadamard. Then we have R2. Then we have this one. I will tell you what the gate R is. Rn. And here I'm going to convince you that this is going to be 0 plus 2 pi I J1 Jn 1. And this is 0. And then so on and so forth. What's this one? That's the last one. And then here we have a hardener and R2. And here we have the last hardener. And this is going to be okay, so now we want to be convinced that this circuit puts indeed the output register in this gate, which is basically the reverse of the quantum Fourier transform. So one then has to do swap to have the order of the qubits as they are here. But so let's see how is defined. This gate R, I write it here. RK is a phase. So basically, all of this is all about implementing controlled phasor operations. So let's start with the first one. Here we have the first Hadamard. So let's follow the first qubit. So after the Hadamard, of course, we have the 0 plus 1 if j is equal to 0, and 0 minus 1 if j is equal to 1. So first we want to write this in a compact way. So then one way of doing it is writing that this is equal to 0 plus minus 1 to the power j, 1. But then another way of writing it is saying that this is e to the 2 pi j1 over 2, 1. I've been writing the same thing. And then this I can write it with the binary fraction. So this one can write with like 0 plus e to the 2 pi 0.j1, 1. That's correct. And that's the first register. So the first qubit. Then, and we are here. Then all the other qubits, for the moment here, I didn't do anything. So basically, if I want to write the multi-qubit state, at this stage, I can write it as, then let's say that this is the state psi 1. Then psi 1 is equal to what I just wrote times all the other qubits in the other registers that I didn't touch yet. Then we apply this rotation on the first qubit that is conditioned on the state of the second one. So it's a phase that depends that we apply if J2 is equal to 1. So then you can understand that I'm going to play exactly the same trick. I'm also going to write that phase in this similar way. So then we write the state here, side 2. This is equal to J2 over 2. This we have been already writing like J1 over 2. So then this one can write in this way. 0, J1, J2. And this you see that we are going to do the exact same thing for all of the registers. So then, because what you do every time is that you apply a conditional rotation of a phase that depends with a fraction that depends on the parameter k, if the state of kth qubit is in 1. So then you're going to concatenate many of these, and then clearly at the end, the first register is going to be put in this state. You see it, no? Because every time you apply this phase, if state of qubit k is in 1, and then you get the binary function. So then in the case of the first qubit, you have all of the rotations, from R2 to Rn, and you get here. Then if you observe for the second qubit, instead, you start having basically the control only from this, so here you have, what was this? N-1, okay, exactly. So for the second qubit, you only go to the rotation, conditional rotation N-1.
From?
Yes.
From where does it start from?
It's also conditioned. This is your question, maybe, no? That there should be a line that goes to qubit N-2 and N-1. No, N-2 is N-2, so it should be the previous one. No, it's okay. No, it's okay. It's like this. No, correct. Yeah. And this is also conditioned here. So it's to say that here you get, maybe we can do some extra step, but yeah, we can compute the,
Excuse me?
yes.
Does it start from R3? Like R3 and goes on till the second line? The first conditional rotation is R3, or is it?
Yes. Here, you mean?
Yeah.
Yeah. Yeah, no, sorry, but no, not R3. If here is L-1, so then it will be, no, that's also R2. That's also R2.
Okay.
It's just that you don't have all the higher order ones. You don't have the Rn here in the second. And here you only have the R2. Okay, so then at the end, basically the state that you obtain is the multiplication of all of this which is not exactly what we wanted because the order is not good. If you compare with the expression that we wrote for the quantum Fourier transform, is 0.jn1. So if we compare with this expression here, you see that the order of the register is completely reversed, in the sense that here qubit 1 is in state of qubit n and vice versa. So then to fix this you need swap gates, but you need an order of the number of qubits of swap gate, and by now you know that you can obtain a swap gate with 3 CNOTs, which was the exercise we did 1 week ago. Or a couple of days ago. And then if we count how many gates we are using, we have, so here they are n, which are exactly n, because this goes from n to 2, and then we have plus 1. So these are exactly n, plus n minus 1, because here we go until r minus 1, plus n minus 2. So if we count the number of gates, is n, so plus n minus 1 plus 1, and this you know that is n plus 1 over 2. It's an exact sum that you can sum. So this is of order of n squared. Plus you need n swap, but then it's something that is linear with n, so it doesn't change the order. And so all in all, you can implement a quantum Fourier transform with n square gates, order of n square gates. And even if it is an unfair comparison, in the recent chunk they compare with the number of gates that are used for the faster Fourier transform that is written there. So this is, let's look at this. So this is the QFT, while the FFT requires 2 to the n. So n times 2 to the n, so it's an exponential number. But as I said...
FFT is exponential?
Yeah.
In gates? You mean, okay.
Yeah. But so as I said, it's a little bit unfair comparison because you cannot really access to the amplitudes quantum mechanically, and also because we don't know really how to prepare to charge in your quantum register the state of which you would like to have the Fourier transform basically. So it's why, as I said before, the main interest of this is to do other things than the faster Fourier transform. Yeah, do you have questions?
I have a question.
Yes.
The state that you have written to the right, is that the output state that you have in the circuit?
Yes, because look, we computed that the first one, the first register we computed, the other are analogous basically. So all of them, they get just less rotations, less conditional rotations. So then they don't have the full binary fraction, but at the end you only have 0.jn. And then I just copied here the product of all the register. All the qubit states at the output. And I compared this to what you wrote here.
So you said that the application of this circuit is to not actually make a Fourier transform, but to play with the basis of the qubits?
For instance, Shor.
Okay.
You use it in Shor algorithm.
No, I'm asking if that was right, if that statement was right.
Yeah, it is right.
But can you put it to any arbitrary phase? No.
Okay, then we can take a break here. and be back in 10 15 minutes.